Okay, so welcome back once again. And today we will have a look at adder in digital logic, which will do the binary addition much faster than its previous counterpart. So the name of the adder circuit or adder logic is called carry look ahead adder, in short form CLE. This is called as carry look ahead adder because instead of rippling through the stages, this logic helps us to calculate the carries in advance. So that's why we call it as a carry look ahead adder. So it doesn't let the carry ripple through the stages. Okay, so we'll see how it does that. So here is a schematic of the carry ripple adder example for the 4-bit adder logic. You can have 8-bit, 16-bit, 32-bit, 64-bit, and so on and so forth. So as an example, in a basic manner, we have taken the 4-bit. So 4-bit adder circuit, each stage is comprised of 1-bit full adder circuit which has got 3 inputs and 2 outputs. 3 inputs are A naught, B naught, C naught, and 2 outputs are sum and the carry out. So what we have seen previously, that you have initial carry in which is can be assumed to be 0, and then you have LSBs of both the words A and B, each of 4 bits in size, and you add the two numbers A and B bit by bit. So A naught and B naught, that produces S naught and C1. Then you add B1 and A1, that produces S1 and C2, and so on and so forth. So here, after adding A naught, B naught, and C naught, assuming C naught is initially 0, if A naught and B naught both are 1, we know that C naught is likely to be 1. That is how the binary addition takes place. So this C naught goes to the next stage, ripples to the next stage. And the sum here is available only when the C naught reaches or ripples to the next stage, that is in this section of the full adder where A naught and B1 are A1 and B1 are present. So then A1, B1 and C1 are added together to produce S1 and C2. Again, S2 is available when C2 goes to the next stage and gets added with A2 and B2. So you see that you have to wait for this sum, all these sums, when the carry from the previous stages are available. Only when then you have these sums available. So this is kind of series addition where carry is rippling through the stages. So obviously it is a very simple circuit, use less area in the hardware. It has less number of stages, so you have less power. However, the speed of addition is slow. So for small 4-bit, 8-bit, 16 bits, it is okay, you can do that. But for large word size, n bit, let's say n is equal to 64 or 128 or 256, which is in modern ALUs, that is the word, then the addition is quite slow because you have a number of delays through its stages and all that. So how to solve this problem? So the problem can be solved by using another or modified logic called as carry look ahead. So we'll see how this circuit will be transformed into the carry look ahead logic. So basically this circuit will be transformed into carry look ahead to improve the speed of the binary addition. Instead of doing series addition, we'll see how we can do the parallel additions where carries are already in advance calculated and sums are available in parallel. So instead of waiting for each carries to propagate, we will not do that. We will use the CLA logic to predict and calculate the carry bits in advance. So what is the basic concept of it? So we'll see that through this slide. So here you see that you have AND logic. Output of the AND logic is called a generate, and then you have XOR logic. The output of it is called as propagate. So we have to do two things: generate the carries and propagate them if they are generated. So for a 4-bit adder example, again you have 4 bits: A naught, B naught, A1, B1, A2, B2, and A3, B3. What we just saw in the previous schematic right over here, all these bits. So for each of these combination of bits, A naught and B naught, A1 and B1, and so on and so forth, what you need to do is you implement this logic. So for each bit positions where AI and BI are the bits of inputs A and B. So here it will be AI and BI, and then it will be GI. You generate this logic, GI equal to AI and BI. So for you have G naught equal to A naught and B naught, G1 equal to A1, B1, and so on and so forth. For 4-bit, you have G3 equal to A3 and B3. That is the MSB. Similarly, so this is kind of uh, if your carry gets generated if both of these bits are 1 in the word A and B. If A and B are 4 bits each, then A and B, if both of these bits are 1, then GI is carry gets generated. And now if that carry gets generated, that gets propagated to the next stage by this logic, where which is called as propagate. So if any one of the bits in the 4-bit combination, AI and BI, if any of these bits in word A and B is 1, then you know that the propagate logic gets activated. It propagates that carry. Okay. So we have this logic implementation, and then what you do here is that you have this carry equation. So when the carry gets generated and it has to be propagated, so the carry for the next stage, that is CI plus 1, is equal to therefore GI, the generated logic, or PI and CI, propagate and CI. CI is the initial carry. Okay, that is 1. So just I equal to 0 to 3 for a 4-bit number size. Okay. So what you see here, there are 4 carry out equations for a 4-bit adder: C1, C2, C3, C4. What you do here is you, instead of calculating them sequentially, you calculate them in parallel. So these equations are already calculated in parallel and they are ready. So these equations are: C1 is equal to GO plus or logic PO and CO. Then C2 is equal to G1 or P1 and C1. C3 is equal to G2 or P2 and C2. And C4 is equal to G3 or P3 and C3. So you have these equations ready, which are basically the carry equations. You see that this is what the equation is: GI plus PI and CI, and for each bits from 0 to 3, you have those equations ready. And now you can expand them. So C1 is equal to G naught or P naught C naught, which is same as here. But for C2, you know that you have the C1 here. So C1 is equation this one, put this value of C1 here, and then you have C2 is equal to G1 plus P1 GO plus P1 P naught C naught. Similarly, C3 is G2 plus P2 C2. So value of C2 is this equation. Put in the value here. After expansion, you have the C3 is equal to this logic. Then C4 is this one. Put the value of C3 from here. And after expansion, you get C4 is equal to G3 plus P3 G2 plus so on and so forth. So what you are doing here, all the carries from C1, C2, C3, C4, which are the next stage carries, are available in parallel after few gate delays. So you have AND gate here, you have AND gate, another AND gate here, AND gate, and then you have a OR logic. So after this basic logic gate delays, you have your carries available for the next stages. Remember, C naught here is the initial carry right here, C naught, that is assumed to be 0, or it could be whatever, assuming it could be 1 as well if you have that coming from the previous stages. But then C1 to C2 to C3 and C4 are what you have here, and after expansion what you have here. So this is how you see that you will have to implement this logic using AND gate, then you have implemented this logic using XOR logic, and then you have to use this combinational logic circuitry to make this carry look ahead adder work. So this is how you calculate all these carries. So, how do we know that we have understood the concept? So, it is simple with the example. So, let's say you have two words of 4 bits each that needs to be added. A is equal to 0111, that is 7 in decimal, and B is equal to 1001, that is 1001, 9 in decimal. And you have to add them with the carry look ahead. You can also add them with the carry repel, but now you will do that with the carry look ahead. So what you do here, you put them in the line and you carry the bitwise operations. So bitwise operations is that this is the LSB of all the two numbers, and this is the MSB of these two numbers. So what you do here, the bit I, that is bit I is equal to 0 up to I is equal to 3, you put these numbers here. So 1110, you put in 1110, and then 1001 for B is equal to 1001. So this is the LSB and these are the MSB. You assume that initial carry C naught is equal to 0. And once you put them, you know that generate logic and the propagate logic have these two equations. So generate logic is for each bit I is equal to 0 to 3. So A and B, obviously you look at A and B, both are 1. That's why GI is equal to 1. And for other, you have you have 0 because one of the bits from A and B, they are 0. That's why the output is 0 here. Similarly, for the A XOR B is very simple. What you do here, output of the XOR logic is 1 if any one of the bit A or B is equal to 1. So here you see that for both are 1, then PI is 0. So this basically you are implementing just XOR logic and the AND logic here. Once that is done, uh, you got these two equations ready, and you have now tasks to compute your carries C1, C2, C3, and C4. So these are the equations we have seen from the previous slide. G naught or P naught C naught. C2 is G1 plus P1 G naught plus P1 P naught C naught. So these values of G naught and P naught and C naught, similarly G1, P1, or instead you say GI, PI, and C C naught actually, they are available from the previous equations we have seen. So put those values 1 plus 0, C1 becomes 1, then C2 0 or 1 and 1 or 0, that C2 is 1, and C3 is 1, C4 is 1. How to verify? So this equation is very simple. You see the examples here. These two are the number A and B, 0, 1, 1, 1. B is 1, 0, 0, 0, 1. You see that these are the numbers A and B, same 0, 1, 1, 1 and 1, 0, 0, 1. This is what we have written here. Now, when you add 1 plus 1, your sum is 0 and initial carry is C naught. We have assumed it to be 0. So you remember initial carry we have assumed it to be 0. So that's why C naught is 0. But S naught, that is sum is 0 when you add 1 plus 1. But the carry got generated now due to this addition. So carry here is C1 is equal to 1. And that's what we have written here. C1 is equal to 1 through this logic. Okay. So now here we are doing this kind of, we are explaining the sequential or series addition by the carry ripple ahead adder. And here we are doing the same implementation using carry look ahead. So C1 got to 1 we have written here. So then add 1 plus 1 again 0. Sum is 0 but the carry got 1. So put it here. C2 is 1. So here also C2 is equal to 1. Again 1 plus 1 0. Sum is 0. Carry got generated which is C3. And here also C3 is equal to 1. Then sum is 0. C4 got generated which is equal to 1. This is a series addition we have done, and this is with the carry look ahead, a parallel addition. We are calculating all those carries in parallel with the logic equations. We only need this combinational logic circuit. C4 is equal to 1 here. And the sum we have seen that from the previous slides, the sum equation SI is equal to PI XOR CI. So you just have to put in those values right here. So S naught would be P naught XOR C naught. S1 would be P1 XOR C1. S2 would be P2 XOR C2. And S3 would be P3 XOR C3. So if any one of these is equal to 1, then output is 1. Otherwise, it is 0. So you see 0 XOR 0, 0, 1 XOR 1, 0, 1 XOR 1, 0, 1 XOR 1, 0. All sum bits are 0. Similarly, here we see that all sum bits are 0. So final result is sum is 0, 0, 0, but with the carry out C4 is equal to 1, which is C4, you put in here as a MSB, result becomes 5 bit, and then that means decimal 16, 1, 0, 0, 0, 0. That is 7 plus 9 is equal to 16. So this is how you see that the carry look ahead adder works. We are calling it as a carry look ahead because it is calculating and computing and making available all carry bits in parallel available at the simultaneous way, so that some bits are also available calculated with the propagate and carry out, with the propagate and the carry out. You don't have to wait for carry to ripple through the stages. So this is this architecture in yellow from the carry ripple adder. C naught goes in, then C1, C2, but you see there is a slight change. C1 is not coming from the 1-bit adder as in the previous schematic. Instead, we have this extra logic box here, which is computing two output G naught, P naught, G1, P1, G2, P2, G3, P3. In other words, GI and PI. Through AND logic and XOR logic, it is computing that. And then there is this extra hardware to compute all these C1, C2, C3, C4, or instead I would say CI plus 1. That is the next stage carries. C naught we assume to be 0. And those carries are going to the stages what you see here with the red arrows right here. So you see that this carry look ahead error needing additional hardware, but it is a faster, efficient circuit. Complexity of the hardware goes up, maybe a power consumption goes up, but due to generation of all carries in parallel, you save a lot of time in carry propagation delays introduced due to the carry propagation, and that's what makes sense. So hope you found this module useful. It is very simple to implement this and or logic here. This is basically a combination of circuits that you can put in this box, and you say that this is how complete carry look ahead adder will be done. So hope you found this model useful. If you did so, share it with others for wider reach. Stay tuned for more engaging content like this. Till then, wish you happy learning.